Okay, so I know the last video was a lot. There was a lot of derivation on delta G, but what we really came to was this equilibrium constant. And this equilibrium constant is a really key piece and probably something that you remember that we worked a lot with in Gen Chem and in analytical. And so I want to go into a little more in depth about what this equilibrium constant is and how we define it. Okay, so in the last video, we came to this equation where delta G equals delta G standard plus RT, ln Q. And we defined Q in terms of these pressures. But remember that in doing this, we ignored this P naught. And so really, this Q expression that we're working with is our P of Y over P naught of Y times P of Z divided by P naught of Z over P of A over P naught of A times PB over P naught B. And so this P naught we define to be equal to 1 bar, but really it can be any reference state. And this reference state is a key thing. So if we say that this, and it really came from that reference state, that P naught came from this definition of the chemical potential, where the chemical potential is the reference chemical potential plus this correction term of RT ln P over P naught. Now, if we were to want to define something simpler than P over P naught, because as you saw, that gets complicated to write, we can say that this term A is equal to that P over P naught term. A is what is known as activity. The activity is really, it's an experimental term, and it's talking about how the reality and the ideal differ. And so we're really kind of normalizing what is actually happening. And the nice thing is that this activity can actually be defined in other terms. And one very common term that we like to use to define activity is the concentration. And so it would be the concentration of A divided by a reference concentration. And that reference concentration is a 1 molar solution. And so this takes into account things like intermolecular forces, things like non-ideality, things like complexation, where our concentration that we actually have in our solution is not exactly what our idealized solution would be. So this activity, this is actually the term that is found in the expressions for K and for Q, the reaction quotient. Now, because the denominator in terms of concentration is 1 molar, or in terms of pressure is 1 bar, we can leave this off and make our expressions much simpler and write these as Kp equals the pressure of A raised to the stoichiometry of A times the pressure of B raised to the stoichiometry of B. Oh, and I did this upside down. but that's okay. Pressure of y raised to the stoichiometry of y times the pressure of z raised to the stoichiometry of z. And I'm going to put 1 over Kp since I wrote this upside down. Or we can say, if we are working with something that is in the solution form, we can say the concentration of A, let's not write it upside down like I did before, the concentration of Y raised to the stoichiometry of Y times the concentration of Z raised to the stoichiometry of Z over the concentration of A, stoichiometry of A, concentration of B, stoichiometry of B. Okay, so this activity is a very useful term, and it's actually what fixes our units for these K terms. And this isn't Kp anymore, we call this Kc. And remember that if we're working with K, we are at equilibrium. Q is when we are at any point in the reaction. So I used this Kc term as the extent of the reaction. And so at any point in the reaction, we can solve for Q. At equilibrium, Q is equal to K. And so if we are trying to find K, we must use equilibrium pressures or concentrations. I hope that helps remind you a little bit of some of the nuances of equilibrium and helps to explain this term that we're going to use every once in a while, known as the activity. In the next video, we are going to be working on temperature dependence and Le Chatelier's principle. But we are almost done with chapter 12, so we're getting there.